And recording. Okay, howdy everybody. This is lab exercise 4 about round robin scheduling. And my name is Min, and I will go through this with you for today. Okay, so LE4 is designed to give you some first-hand experience on how simple CPU scheduler processes work jobs. LE4 will have you completed a round-robin scheduler and process a list of jobs from a CSV file. So what is a round-robin scheduler? Well, you can think about it as a how you deal cards, right? You usually go through in a circle. You don't just give all the cards to first person and then all the cards to the second person and so on and so on. You go one at a time. So 1, 2, 3, 1, 2, 3, 1, 2, 3, so on like that. So a round robin process scheduler does the same thing where it's give the time ticket to the first. Let's say you have 3 processes. It gives 1 to the first process, second one, third one, and then it asks 1, do you need 1 more? It's like, yes, okay, give me 1 more, and so on, until it has everything completed. And how long? And that ticket expires after a certain amount of time, so that one process don't hog the entire thing. So that time range right there is called a time quantum. So let's say if you have a time quantum of 3, then the process can work on the CPU for 3 seconds, and then it must be kicked out so that the next one can come in and does the same thing. Okay. So let's see. LE4 expectations. The goal is to create a function round robin CPU scheduler program. Okay, it takes in a CSV input file containing the task, arrival time, burst time, and time quantum. Output a per second report on which process is running. All of this you can see right here. Here's a table, okay, and I will have a little MS Paint right after so that you can see. And then what happened is then you have the PID right here, the arrival time and the burst time. So let's say the PID 1 arrive at the 0th second. So then it's the first one to go. So you can see 0, 1, and so on and so on. And then because the time quantum is 3 right here, that means it can go through all, process 1 can use for 3 seconds, the CPU for 3 seconds before it kick itself out. Well, but it's just happened that this one is finished the job after 3 seconds, so it still get kick out right here. But you can see in process 2, it can kick out after 3 seconds, and then so on and so on. Okay, the program should be able to print out which job is running every second that the CPU runs until all the jobs are completed. The program should use the time quantum and the remaining time jobs of the jobs to preempt or stop the active action. Here's the, if you ever confused about the output of this, you can go to your code right here. Actually, let me go to, this one right here. So I have the file browser right here. And if you click on test files of this one, and then you click on, I think, let's see, test file. There you go. Let's say you click on output long. You can see here's an output of one test that you have to do make test. You can see running, and it run and stop and run and run. It's finished its job. So it should be print in this format. But thankfully for you, I think it is in process.cpp. So you can see this file are created for you, and you can use this to get things that you need for the processes. You can go to, I think, roundrobin.cpp. These are the only 2 you need to do, and I will go through them after an example. But you can see they're pretty simple. Okay. I think it's under scheduler. Okay, let's see. Print help. You can print help right here. You can also process arguments and so on, and main and so on. And I think in .cpp there's a lot of things you can do. You can print, so you can look into how the print function works. This one is to print if the PID is if it's -1, which means nothing is there, then just print no op. So no op, no op, no op, no op. So if int PID equal to -1, just print knob instead for how many ever seconds that need before the next one comes in. Else you just do the is completed. If it's true, then it says it's finished its job. You have to, put in the true and false right there, and the PID is the PID that you DQ is from. So before we go to the code again, let's go back to here and let's talk about the example. Okay, so here is the example, and apologize for my skilled Paint, MS Paint. I wouldn't say it's the most skillful one, but hey, we take what we can, right? Okay, so here's the time quantum. You have the time quantum of 3 right here. Here's the Q, right? You can see it's a Q right here, 1, 2, 3, 4, 5, 6, 7, 8. You can see that here's the arrival time, and here's the burst, and I make a cross right here to check how many the time remaining of each. So let's go through this together, okay? So PID 1 arrive at 0. So here you go. It queue into 1 and then immediately get DQ'd because so it got DQ'd and then it started running on the CPU. So from 0 to the 0 second to 3 second. It takes the whole thing, and it's just that this also takes the burst time takes 3 seconds. So it finished after 3 seconds. So now it got now we have the process will ask the question, does it need to be enqueued again? And because the time remaining is 0, it can just no, it can be dropped. So 1 will be dropped after the 3 seconds, and then 2 you get queued at 3 seconds. So now it's go in, immediately get DQ'd so that it plug into the CPU. So now it runs from 3 seconds to 6 seconds, okay? But at the same time, at the 4th second, 3 and 4, process 3 and 4 comes in, get enqueued, and because it comes in at the same time, I think in theory 3 or 4, whichever one get execute first. But for the sake of this one, I get 3 first and then 4. Okay, and then at 5 seconds, the 5th PID comes in, or PID 5 comes in and get enqueued again. So now 1 is enqueued. I mean, 1 is DQ'd and gone. 2 is DQ'd and it's running. And during that time, 3, 4, 5 got enqueued. Okay. And then at 6 seconds, 2 get DQ'd because the time is up. Time to get out of here. So it got kicked out, and now immediately 3 and 4 got DQ'd. I mean, 3 get DQ'd so that it can get into the CPU. So then at 6 seconds, 3 start executing, and then it get kicked out at 9 seconds after the time quantum. You can see also that I forgot to mention that, hey, 2 right here, right? It has 4 seconds, so now it's go down to 1 second. So it needs another second left. So again, it gives the time ticket. And now it's like, okay, so now you need 1 more second. Okay, I'll give you the time quantum of 3, but the moment you're done, you get out of here instead of staying here for 3 seconds. Okay. So then 2 will get another time ticket. Or get enqueued again at the end of the queue, right? Because when you push something to the queue, it get to the end. It stay at the end. Okay. And then you go to the 6 one, and then you can do it's 2. Go to 9, then 3. It kick out again at 8 seconds. 6 got enqueued again, and then 3 kicks out at 3. 3 got kicks out, and 4 comes in to do its job. So 4 comes out in at 9 seconds, get executed from 9 to 12. So at 12 seconds, 4 gets out of here, but also 8 gets enqueued again. It doesn't matter. It's still at the end of the queue. Both 3 and 4 now, at 9 seconds, 3 get back into the queue. At 12 seconds, 4 get back into the queue. Okay. And then at 15 seconds, 5 got kicked out, because now 5 is right here. 5 got got kicked out, and you can see it takes about 2 more seconds. So again, to get a time ticket, so we have to put into the queue again. 18. At 18 seconds, 6 got kicked out. Okay, it's done. It's like, nope, you still have time, but you gotta be at the end of the queue. So 6 got out, put the end of the queue. 3 more seconds later, again, time quantum, 7 got kicks out. and then put in a queue. And then this is where interesting things happen. Again, as I said before, is even if we give you the time ticket of 3 seconds, or the time quantum of 3 seconds, if you just need 2 seconds to do it, you do it for 2 seconds, and then you'll be a nice person and let other people use the CPU, right? So in this case, 8 get executed at 24 here, right? The 21st second get kicked out at the 23rd second, because you know it's done. It's like, hey, I'm done. Now I give it back to the other person. So the first person in line again, which is because 1 is done, so it's gone, is 2, right? The first person at the 20 kick out at 20. The third 2 comes in again. 24th it gets kicked out because it's done, right? It just needs another second. It's like, oh, I'm done. I just need another second. Now I'm done. So 2 get kicked out at 24 and get dropped, like it's gone. And then 3 comes in, get execute for 2 more seconds right here. 5 minus 3 is 2, okay. And then it got kicks out again. 3 got kicked out. And then 4 comes in at 26. Okay, 4 comes in at 26. It takes 3 seconds, so it's gonna be done at 20. I'm sorry, this is 24. 24. Hang on, 24 right here. 24. Okay, 23 comes in, takes another 3 seconds. Yeah, 26. Okay. And then 4 comes in. 4 should take 3 seconds. My apologies, it should take 3 seconds, so 29th, but for some reason I did 28. So, you know, it's actually 29. So 5 should be kicked out, 4 should be kicked out at 29. It's also done. So now 5 comes in. 5 comes in, and it takes about at 29th. It takes about 2 seconds, so it will be done at 31st, not 30th, 31st. Please, sorry, this should be +1 here as well. So 31st, that's 31st second, it got kicked out, and 6 come in and does that. But you know, even if I accidentally add the wrong numbers, you can see that the thing is this, the concept stay the same. Is you keep getting in, you get the time you need, you do the thing, and then you got kicked out. Okay, and they are in a chronological order. It's from the first one that comes in to the last one that comes out. Okay, it's just in a queue, right? If you need to go, you ask again at the end, at the front of the queue, once you're done the CPU, do you need more time? If you do, go back to the end of the queue and then wait until you're first in line again. Okay. Okay, so the starter code, you're provided with the process class in process.cpp, round robin class in round robin.cpp, and the main function in schedule.cpp. The only file that you need to modify is the round robin.cpp. Modification scope is limited to constructor, the round robin class, and the schedule task. You know, student asked me if I really need to change anything else. It's not necessary, but let's say for debugging reason that you have to change something, I guess you can, but it shouldn't take too long to do it. So yeah. Resource for the lab, well, of course we recommend covering process scheduling, particularly round robin. For this semester in particular, fall 2022 with Dr. Kibo, he hasn't covered in class yet, unfortunately. But you can always look up round robin. It's really simple. Google it, and I mean, if you just Google it, I've Googled round here, and you can see here's the definition for round robin. It's not that bad. Okay. Yeah, it's just, and you can round robin scheduling if you want, and it will give you the whole thing. Like the Wikipedia page is pretty helpful. And then you can look over the shared pointer. This is more particularly for C++. but you're more, it's a way for you to use point. You can still pass pointer around without having to deal with. It's part of smart pointer, so you can Google smart pointer. But the whole goal is to be able to do pointer arithmetic or pointer operations in general without having to deal with new and delete, which some people might prefer, but it's a C++ specific syntax, so if you can't really use it in C, okay? At least to my knowledge. Okay, and of course, ask question on Discord. If you're from Dr. Tiagi's section, ask on Teams. Honestly, at the end of the day, yeah, just ask question if you need help. Okay. So let me go over the last part I want to show is exactly what you need, what step you need to be able to do this. So again, you have two files that you need to change. Two functions rather, methods if you want to call it that way, but I call it function. Anyway, you have a round robin. In here you just extract info from the file, extract process info. Look that you basically just pass in the name of the file, the path to the file to this function right here. You can look around and you'll be able to find where extract process info is. And then you initialize the time quantum. So the round robin class has a time quantum data member. Basically, it's how big the time quantum is. So you can just pass the time quantum right here. And then for the round robin schedule task, so this is your main function that you'll be able to test. You see that you need a variable to keep track of the system time, because you need to be able to print out, nicely like this. So it's just a global, quote unquote global, not really. It's like within that scope, but before the while loop, a way to track things. So nicely for you. There you go. Okay. And then you iterate until all processes are complete. So basically, you just keep having a queue, and then people just keep going back to the queue if they need more time, and so on and so on, until they're done. Okay. So inside the while loop, so while the queue is not empty, go to the next non-complete process. So just dequeue. So just pop the top of the queue. Okay. So pop it off the queue. Run process for time quantum. Unless there is less time, so use the min function. Okay, so you have the time quantum and maybe the amount of time left. So there's a function for you to be able to get this. I think that function is get time quantum. Oh no, sorry, not that one. I think it's under process. Let's see, where's process? Right here. So you can get the process, and you can get arrival time, get burst time, get remaining time. This one, yep, right here. So you have a min function that will get the lower of the two. So either it takes 2. Let's say you have the time quantum of 3, then it might take the get remaining time of 2. Then it will choose the remaining time. So it runs for 2 more seconds, and so on. Okay. Let's see. Where's my process again? Oh no. Sorry. Oh, right here. Yep. Oh, nope, not this one. Where is it? Schedule. Oops. Oh. Where is it? Oh, round robin. Sorry. It's like, you can see it's 8:46 and I'm tired. But yeah, it's okay. But you can see that you run the process of time quantum, and then you wait until the arrival time of the system ahead and print knob. So again, you have a special print function, so you don't have to deal with anything. But you can set the the PID equal to -1, right? The system time you just pass in, then is complete is equal to, I think it's equal to false. Yeah. It's equal to false, so it's running. So knob right here. You keep printing knob, okay, or no operation, okay, and then print each system time step. So you can just print whether you update. Basically, you update this so that it looks like this. Looks like, okay, and then you update the number each system time step. Yep. Update complete process. So either let's see, either you ask if you go to the let's see, where is the round robin at? Right here, process CPP rather. Okay, so you ask is this process completed? If it's returned true, you just drop it. You don't do anything with it. But if it's false, then you put it back into a queue, right? If it's true, the one thing I forgot in looking at this is that you have to print out the last update that is done, right? So if it's done, you print out it's done. Else, you just put it back into the queue at the end of the queue, so you push it back, okay? And after you've done that, you compile, you can test around, and here's one way you can test it. So all the test files are in test files right here. So you just read the CSV file, not the TXT file. The TXT file is the output, the expected output. So you want to get the other one, you do the testlong.csv. So I have it right here, and if I enter, you can see that it runs like this. You can just go like that. It's running, it is running, it is running. It's good, and it's all good. Okay. So yeah, you can test the one with NOP. So let's do the one with NOP. Test NOP. Okay, and you can see it's running, and then say no op is running because there's nothing. But you can not running. Okay, so you do is running right here. So make sure in the print function that you set is complete to false, right? Because then it can print something like this out. I mean to false right here. Yeah. Okay. So that's it. It should take you I expect it to take about 20 minutes, 30 minutes, and about 12, 15 lines of code. But I wish you the best. Thank you.